Okay, I'm back with nuclear fuel cycle part two. Where were we? We were at the talking about the European pressurized reactor, the example. Well, we're talking about a normal, average water-cooled reactor, and we use the metaphor of a log burning. Like I said, you have the 5% log, the 5% kindling or branch, 95% log, and 65% of that log, that branch becomes ash. Immediately goes to fission products, which is what the ash is, the fission products, and the branch is uranium 235. The log is uranium 238. About 2% of the total mass changes into uranium 239 through a neutron capture, and then it emits two stages of beta decay. One becomes neptunium 239 and then plutonium 239. And in this metaphor, plutonium 239 is the charcoal, and any higher what's called transuranic or actinide. These are also, in my metaphor, charcoal. So the plutonium sitting there, the plutonium 239 is like the uranium 235. You can smash it in half and it burns, and it generates a load of products which are about roughly half the weight, but there's a degree of randomness around, which is the fission products. So the upshot is, at the beginning of a fuel cycle in, say for example, a reactor which starts at 5% uranium 235 enrichment, such as a EPR, is that the beginning you have 5% uranium 235, 95% uranium 238, and by the end of the cycle you end up with about 1.7% uranium 235, and about 3.3% of that uranium 235 has been converted into ash or into fission products, and the 2% mass which becomes the plutonium 239, about half to 3/4 of that ends up getting consumed and becoming fission products. So at the end of the fuel cycle you end up with about 93% of the original uranium 238, or in my metaphor, 93% of the original log. 93% of the total mass is original unburnt log. You end up with about 1.7% of the total mass is the original unburnt branches and kindling, and about 5% is ash and soot, and that 5% comes from direct burning of the kindling and direct burning of the charcoal, which is the transition from the log. So you change the percentage. So for example, some reactors start with a slightly higher percentage of enrichment, so you might start at like 6 or 8% kindling to 92% log, or you might end up like 3.3% of branches to 95, 96, 97% log. And in the CANDU reactor, which is the most efficient of all the reactors optimized for burning uranium 235, you can start with 99.3% log and 0.7% branch, the original natural ratio. And by the end of that cycle, you would end up with probably around about 0.35% unburnt log remaining, and maybe 0.2% that's either transitioned to become charcoal and then burnt, or just transitioned to become charcoal and been unburnt. So that's so what happens is that you then, once you put the fire out, in this metaphor, you still have all that stuff. Only a small portion of it is actually burnt, and you can come back to that later on. And there's a number of, now most reactors are what's called thermal spectrum reactors, and these are branch burners or kindling burners. At the beginning of the nuclear era, there were two different types of different ideas of reactors. One was thermal spectrum reactors, which are branch or kindling burners. Furnaces optimized for burning uranium-235. But there was another type of well, not just one type, but multiple types, but a category called breeder reactors. And if you had to sum up what breeder reactors are, they are primarily log burners. And it made sense to burn the log because, yeah, it's more involved because you've got because there's several steps. So, for example, but the advantage is you got about 140 times more of the original resource, which you can go after. Now, another way of thinking about this is another metaphor. It's just the way I think, so bear with me. Is to understand how the nuclear industry works. Think of it how the oil industry works. In the 1850s, you would oil was discovered, 1860s, 1870s, and the original use for oil was to replace whale oil, in which they used whale oil to burn for light at night, and this essentially put the whaling industry out of commission. And the internal combustion engine was developed, and the internal combustion engine was developed from the most volatile component that could be separated from this oil, but there was a lot of waste product. So along comes Frenchman Rudolf Diesel. As the name suggests, he's the inventor of the diesel engine. So out of a gallon of oil in America today, the ratio is probably different back then. A gallon is 42. It's not a gallon. I mean a barrel. I stand corrected. Sorry, a barrel of oil, which is 42 gallons. About 22 gallons becomes petrol, or Americans might use the term gasoline, I think. And about 11 gallons becomes diesel. So basically the question is, the whole point of what Rudolf Diesel was trying to do was he was trying to build a motor that could utilize a previously unused waste product. This was the whole idea of the diesel motor. So the question is, what's better, diesel or petrol or diesel motors? Both. You need both, because the whole point of both is they work together to fully utilize the resource that you want to use, and the rest becomes all the other products that are made, everything from chewing gum to soft contact lenses, which is all the other, or lubricant oil and lubricant grease. So basically, diesel and petrol motors have they work together to utilize the available resource. So this situation is similar to how it works with uranium, but it's much more lopsided. So like I said, when you dig uranium out of the ground, 99.3% of it is uranium-238, and the 0.7% is uranium-235. So in this metaphor, basically uranium-235 is petrol, and uranium-238 is like diesel, a lower volatility product. So at the beginning of the nuclear era, reactors had, even to today, you have to choose what you want to go for. So the reactors optimized to go for uranium-235 are called thermal spectrum reactors, and uranium reactors designed to optimize to go for uranium-238 are called breeder reactors. So breeder reactors are kind of like the diesel motor equivalent, and you could use diesel, but the upshot of it is we just went out and found more. Because it's so compact, we just went out and found more uranium. And so for various reasons, both legitimate and political, thermal spectrum reactors have become the most popular. But it's always been, since day one, the belief that we would have to go back to, when I say go back, because the very first reactor that ever generated electricity was called EBR-1, Experimental Breeder Reactor 1, which in 1951 lit 4 200-watt light bulbs, and that was a sodium-cooled reactor. But the upshot is that thermal spectrum reactors won out, and here we are. But it's always been believed that we will at some point go to breeder spectrum reactors. Now okay, now I'm going to jump back to the log burning metaphor, because the petrol diesel metaphor kind of runs out. But okay, so the beauty of with my original metaphor, furnaces either can be optimized to burn kindling or branches, or they can be optimized to burn log, the bulk of it. So we've essentially built mostly kindling burners. So what happens is, like I said, is at the end of the cycle, the vast bulk of unburnt log and even a substantial portion of unburnt kindling, that's what's used nuclear fuel. Let's use the term used rather than waste or spent, because it's nowhere near spent. So, and also the tailings themselves. The tailings still have about 0.4%, 0.4% uranium-235, or 0.3 or 4% branch to 99.6% log. The materials, these waste product materials, have tremendous recycling potential. Possibly the greatest recycling potential of any waste product from any industry humans have ever created. I mean, you think of like a reactor, for example, might have 100 tons of fuel assembly. The fuel assemblies inside it may weigh 100 tons, and they get rotated on a third base every 2 years, whereas a third comes out between 1 and 2 years, and then another third of that, 30 tons goes in. So basically each third section or 30 tons group of fuel assemblies